Hello everyone, this is Unal, and I'll talk about the effects of the black hole spin on the fundamental plane of black hole activity. So fundamental plane is uh, a correlation basically between the uh, accretion power or luminosity and the jet power, which is sometimes called jet disk symbiosis. So these both accretion and jet powers are could be expressed some power laws of accretion rate and the mass of the black hole and possible spin. But in the initial original relation, which was hidden, jet power is typically probed by radio, and the accretion power is by some X-rays or O3 line or some other probes. So since you can express these guys as such power laws, you can end up with writing an equation, which is a linear equation in log basis. It becomes a plane equation. And observationally, this relation has been found by these two groups. On the y-axis, you see the radio power, and on the x-axis, you see X-ray luminosity and the mass. And there's an overall coefficient that has been set to get the minimum scatter. But even if you see that this line really fits well with these data points, there are factors of, there's 3 orders of magnitude or even 4 or 5 orders of magnitude deviations in the in some data points. So we realize that even if you have the same mass and X-ray power, the radio power, or in a way jet power, could deviate, like let's say 3 orders of magnitude. So this motivated us to suggest a new variable for the system. And we first started, since the fundamental plane has 2 legs, one is the accretion power, the other one is the jet power. We started with the spin dependence of the disk luminosity or accretion power. So typically, the radiation coming from the disk has been calculated by the energy radiated until the innermost stable circular orbit. So if the black hole spins faster, these ISCO radiuses come closer to the black hole, and you could radiate more energy. And if they're rotating the retrograde or the low spin, these guys are far away, and then you radiate less energy. And this has been tried by the Bardeen many years ago. So for the when one wants to study the spin dependence of the jet power, one can start from the Blandford-Znaiec formula, which basically tells that after some simplification, the jet power is proportional to b square, the horizon square, and the horizon speed. So the horizon speed is definitely spin dependent, and the horizon size as well. But the spin dependence of the magnetic field has not been worked out well until now. It has been estimated either some basic cosine function, but its spin dependence hasn't been worked out. That's the thing we especially worked on. So we started with the magnetorotational instability relation, which connects the B field and the typical specific angular momentum of the particles. Then using number density conservation and the specific angular momentum of the particles rotating around the black hole, we estimate the magnetic field in terms of the spin value of the black hole. So as you see here, B square is proportional to m dot as usual, but we have this specific angular momentum square, which is again dependent on the spin value, and the S is the dimensionless value of the R-ISCO. You can imagine it R-ISCO divided by GM, and it's also proportional to L Eddington. So when you take this relation and this jet relation and plug in the B field, you end up with this really highly nonlinear and non-trivial spin dependence. And it's interesting that even in the slow spin values, you see the quadratic proportionality, this spin dependence grows very fast and non-linearly. And even in the very high spins, it goes with omega to the 6, which is interestingly matching perfectly with the various simulations done by Tolkovsky and McKinney and Narayan. So then one can relate the earlier relation of the fundamental plane as a spin modified fundamental plane, and you introduce or incorporate the spin dependencies of the radio power and the X-ray power. Then since in the fundamental plane relation there is just some this spin dependence completely ignored, you can define these scatters as a generic way, in such a way that you define such that fundamental plane relation gives that the scatters are zero. But for the spin modified case, there's a spin dependent part, and which allows you to generate scatters in this case. And then as you see, this delta parameter, which is defined as fundamental plane, gives you a zero scatter like this way. Green points indicate the data points, and the blue ones are the spin modified fundamental planes predictions. And these error bars are coming from the error bars in the spin value, which is translated to this delta. Or in another way, you can imagine this problem from again the same fundamental plane relations variables. X-axis is just a combination of, again, Lx and the mass, and the y-axis is Lr. And this is the standard fundamental plane relation. And look at these scatters for the 10 AGNs whose spins are measured precisely independent measurements by continuum and some spectral techniques, and not they are not an independent variable, but just inherent property of the system. And here in this bottom plot, we see that again the same x-axis, but on the y-axis we incorporate the spin dependence of Lr and Lx, and we write it in such a way that this delta includes all spin dependence of this problem. As you see, pretty much all the data points given as red dots come closer to this prediction. There's a huge improvement in the standard deviation from 1 to typically 10 to 0.5. So as a last point, and maybe as some problem we try to finalize with Fabio and Avi, you can also use this relation as a spin estimator, such that when the other variables are given, you can extract out the spin value of the AGNs. And if you could determine the spins of or put lower bounds on the spins of the very heavy AGNs, it allows you to probe very light degrees of freedom, bosonic degrees of freedom, as long as their Compton wavelength is proportional to the horizon size. This allows you to rule out or probe some parts of the parameter spores of light particles. We are now probing some very interesting range which has been not probed before. We further also constrain the energy density of such particles less than 10% for given ranges. That's a lot. That's it. And thanks a lot for your attention.